Yes. Eventually. Now, notice what the heading is of this section on this PowerPoint. It was changed between the second edition and the third edition of the book, but that heading is what we're going to do in Tuesday. That's the most important part of 9.5, is convergence at the endpoints. That you will see on the number 6 questions on the College Board test is often something you're asked for. So we will focus on that tomorrow on the beta lesson. This is from 9.4. When you use the ratio test, we're concerned that if the n plus 1 term to the nth term is less than 1, it's convergent. If it's greater than 1, that means the middle term of the H chart's getting larger, so the series is divergent. And if it equals 1, the test is inconclusive. The integral test, okay? There are additional tests, except what? The most important test is the ratio test. What does the integral test mean? Well, if you anti-differentiate this, here's an example. Does this thing converge? Which is improper integration. It's giving you a constant. What is that telling you? That the integral converges to the series converges, but doesn't have to go to 2. It just means it converges. P series. See, the P series test is very important to the endpoints. The P series refers to the harmonic. So look at that expression. If P is 1, all those exponents were 1. You'd have 1 plus 1/2 plus 1/3. The harmonic series, there it is. That's the P series where the P is 1. Now, if you look at this, in the middle column of the H chart, the values are going down. So the nth term test is a test for divergence, which doesn't diverge by the nth term test, where the middle column is going up. Middle column of the H chart. It's going down. But even though it's going down, this thing diverges. Barely, but it does diverge. That's important, okay? You need to understand this. The harmonic series diverges, and we're going to use that to compare things. So if I go back here to yesterday or the last week's PowerPoint, Ready? The bottom picture, think of this. The red term. The red is the, think of the red one as the harmonic. So if this thing we know diverges, the red one, then the blue one has to. When you compare something, right, if you're comparing it for a P series, the red one represents the harmonic series. You knew, we're telling you this, the harmonic diverges. So if some series is higher than that, it necessarily has to diverge. See, this picture is kind of helpful, it's very visual. But here it's saying the red thing converges. Here in the top picture, the red one converges. So by definition, something below that must converge. The bottom of the opposite, the red one diverges, so something below it might converge, but something above it has to diverge. And you could go back to that one screen on the 9-4 PowerPoint, help make sense of this to you. So when it says the P series is easy to evaluate, we use it to compare another series. That's like that picture. The harmonic divergence. So we compare that to another series, and if the other series is higher than the harmonic, it necessarily has to diverge. I'm not so much concerned about that. Let's look at this example. Now, what do you notice here? The terms are getting smaller. You just have, it tells you, you got ready, you've got odd numbers in the numerator, 3, 5, 7, 9, and you've got perfect squares in the denominator. 2 squared, 3 squared, 4 squared, 5 squared. But 5/9 is smaller than 3/4. So the terms in the middle column are getting smaller. But that doesn't mean it necessarily converges. So what did they do? They took the leading terms. If you expand this thing with a lattice, you would get n squared plus 2n plus 1. And that's going to take on the behavior of the leading terms. And you would have 2n and n squared. The n's reduced, you would have 2 over n. But 2 over n is larger than the harmonic. So if the harmonic diverges, then this thing necessarily diverges. See, if we do the test for divergence, the nth term test, it doesn't work for us because these terms are getting smaller. The nth term test is kind of silly. It's saying if the middle column, the H chart, the terms are getting larger, the thing diverges. Well, that's common sense. It's the problem we have is when the middle terms of the H chart are getting smaller, make a decision, is it diverging or converging? So in this case, we compare it. What do you got here? It's growing without bound. You can lobe it taller. You're going to get this. You're going to get 2 over n, which is larger than the harmonic. The harmonic, think about those dots. The harmonic diverges, so this 3a must diverge. I would just stop right here. It's bigger than something we know that diverges. But this, the middle term's getting smaller. What do they do? That's a P series. I'm sorry, it's a geometric series. We have 1/2 times 1/2 to 1/2. It was like Zeno's paradox. We're saying that thing's going to 1, so this thing would not necessarily converge. Yeah, this is good news. If the middle term of the H chart, if the absolute value is getting smaller and the signs are alternating positive to negative, it necessarily converges, which is telling you what? This is the alternating harmonic. Denominator, 1, 2, 3, 4, 5, 6. Except if I had 1 plus 1/2 plus 1/3 plus 1/4, we know that that diverges. But if the signs alternate, it converges. Well, that's a big deal. Because what? They're the things we're going to use for comparison. The harmonic diverges. The alternating harmonic converges. You're going to need that tomorrow for the endpoints. What are the big deals here? The harmonic series is a big deal, and the ratio test is a big deal. And how to build a Taylor series is a big deal, which is f of 0 over 0 factorial times x to the 0 plus f prime of 0 over 1 factorial times x to the first plus the Clorentz series. That, not negotiable. What do? We slide it 8 units to the right. We get a Taylor series. The ratio test is a big deal. The harmonic is a big deal. So those 3 things, and then tomorrow, the endpoints will be a big deal. Now there's a document in Canvas that has a summary of chapter 9, but they're the most important components. It's not absolutely convergent. Why not? Because the absolute value of this is the harmonic, which diverges. So it's conditionally convergent, conditioned on the signs alternating. Now, see if that makes sense to you. It's in the box. Write down what's in the box. Kidding. Ready? Think this through. If it's converging, alternating. So if the terms in the H chart are getting smaller and the SIGN is alternating, then the next term. So just think about the easiest way to do that is alternating harmonic. 1/3, 1/4, 1/5. If you start at 1, stop at 1/5. And the next term is -1/6. Then that's going to be the largest possible error. Because after -1/6, it's going to be +1/7, which is going to work against that -1/6. So the error is going to take on the sign of the SIG of the next term, and that would be the maximum amount. You don't have to do Lagrange. Okay. So here's the question which we'll deal with tomorrow. You want the interval of convergence for this series. Which is not really a difficult question, but we'll get to it tomorrow. So here's 3 examples. Integral test in example 1, limit comparison example 3, alternating series test in example 4. We're cross-referencing for you what's in the book for this section. So a couple things. Let's start at the bottom. This is the P-series test. So this P is the exponent, 1 to the P is still 1. So I can rewrite it like that. It converges if the exponent is bigger than 1. So think about that. If this was a 2, then the denominator is getting bigger. If the denominator is bigger, the value of the fraction is small. It's diverging, though, if the denominator is small, and if it equals 1. I'm not getting involved in the alternating series yet. We come up here. What are we looking at? Same thing. Now this thing here is from 1 to infinity. From 1 to infinity. This is from 0 to 1. So here's example 1. We're just going to go through this and do the integral test. They want to know if this thing converges. So we anti-differentiate it, and you get this. Ready? And then what happens? This was on the PowerPoint. You would have small over large is going to 0 plus 2 is 2. So the integral goes to a value. So the series must converge. Not necessarily to 2, but it must converge. That's what you're being asked. All right? So that's your model. We're going to pause the video and ask you to do problem number 1. All right, so what happened? Well, this one's going through the ceiling. It has no limit. N to the negative 1/3, if you anti-differentiate x to the negative 1/3, b's growing without bound. So 2/3 of that doesn't matter. Things growing through the ceiling. So necessarily the series diverges. 3a, this was on the this is the example that was on the PowerPoint. So we're going to compare this thing to the harmonic. What do we get? And this work right in here, what are you doing? I'm multiplying numerator and denominator by 1 in the form of 1 over x squared divided by 1 over x squared. It's the same thing as if you L'Hopital. Okay? So this thing is larger than that, it necessarily diverges. And this is the other example in the PowerPoint. That's just the work that you saw on the PowerPoint. Where you compare them to different things. So these are P series, ready? This one diverges. This is not a piece here, it's geometric. It's 1 over half, 1/2 times itself. That converges. Okay. So we'll pause the video again and ask you to go to problem number 5. Something we know diverges. This thing is bigger than that, so it necessarily diverges. All right. So